Hello everyone. In this video I'm going to be going over 3 examples in which we're asked to solve a linear differential equation by a process known as the variation of parameters. Now I'm not going to go into the development of the process. You can read all about that. It's pretty involved. It would take a lot of writing, a lot of time to do in this video, so I'm not going to do that. I'm just going to show you the procedure itself, the final procedure. Alright, so this example and all 3 examples that I have in this video, I'm asked to solve the differential equation by variation of parameters. Alright, so first, in order to perform this variation of parameters procedure, I'm going to get my differential equation into what's known as standard form. So basically, where the coefficient on the highest order derivative is 1, I'll call it the lead coefficient here. Okay, and like I said, what we're doing is we're going to first get in this standard form for a linear nth order differential equation. So it looks like that where you have 1 times the nth derivative of y with respect to the independent variable, in this case it's x, plus then some function say p1 of x times the n minus first derivative plus all the way down to plus some function of x p sub n minus 1 times of x times y. Alright, where again the coefficient in the highest order derivative is 1. Then all the other coefficients are functions of at most the independent variable. And then on the other side equals some f of x. Right, so that's step 1, which this already is. Alright, you have 1 y double prime plus 0 y prime plus 1 y equals secant x here. Right? So this this secant of x is what I'm calling f of x, the function f of x on the other side here in standard form. Alright, so then I'm going to find what's called the complementary function, and you may have seen this in previous videos of mine. The complementary function is just the general solution to the associated homogeneous equation. So I'm going to say solve the associated homogeneous equation, because right now this is a non-homogeneous, right? You got secant x over here, but if I turn that secant x into 0, that will be our associated homogeneous equation. And that looks like this, y double prime plus y equals 0, and this is one of those linear homogeneous differential equations with constant coefficients. If I let y equal e to the mx power, we get the auxiliary equation, or the characteristic equation, m squared plus 1 equals 0, and the roots of this equation, one of them is I, right, the square root of negative 1, and the other one is negative I. And from all this, you could state the fundamental set of solutions, but I'm just going to go to the general solution right away. The general solution, which again I'm calling YC for the complementary function, the solution of the associated or complementary homogeneous equation, is some constant C1 times the cosine of x plus, and then some other constant C2 times the sine of x. And again, hopefully you remember solving homogeneous equations like this with constant coefficients. What happens when you get complex conjugate roots. Okay. Now, the general solution of the original differential equation, then hopefully recall this, will look like this. Y equals this complementary function plus a particular function, a particular solution, sorry. All right, this y sub p. This is a particular solution, a specific solution to the differential equation. So I have the complementary function, right, the solution of the corresponding homogeneous. The next goal then is going to be to find a particular solution to the non-homogeneous differential equation. All right, and this is where the variation of parameters comes in. So part 3. Vary the parameters, variation of parameters. And what does that mean? Well, in the solution of the homogeneous equation that corresponds to this, you have two parameters, right? C1 and C2. Those are constants. Well, rather than having them be constant, let's have them vary with x, be functions of x. So the form of the particular solution, yp, is going to look almost exactly like this yc, but instead of constants, we're going to be finding a function u1 of x times the cosine of x plus another function u2 of x times sine of x. And my goal is now to find this u1 of x and u2 of x. Right, just again replacing the constant parameters with functions that vary with x. Thus the title, variation of parameters. Alright, so how do we do this? Well, again, I'm not going to go into the development of the procedure. I'm just going to go through the procedure itself with each example. So back in the complementary function, you had cosine x, you had sine x, right? You had two independent solutions to the associated homogeneous equation. So you find the Wrons scheme of the independent solutions to the homogeneous. To that associated homogeneous equation, associated homogeneous. So remember that would be W of, and then the two solutions I got for the associated homogeneous equation were cosine x and sine x. Alright, so hopefully you remember what the Wrons scheme is, and again I'll just call this W. And this was the determinant of a matrix. In this case it would be a 2 by 2 matrix, where in the first row I write those two functions, cosine x, sine x, and then in the second row I write their first derivatives, negative sine x and cosine x, and this would be cosine squared plus sine squared. And for any x, that's going to be equal to 1. Alright, so the Wronskian is 1 for any x. Then, to find this u1 and u2, again, I'm not going into the development. u1 and u2 are going to be functions such that u1 prime is equal to w1 divided by w, where w1 is the same as the Wronskian, but you replace the first column with 0 going all the way down until the last row, and the very last row you have f of x, which way back in the beginning here, f of x was the secant of x. So 0's all the way down to the last row, where in the last row you have f of x from the very beginning when I put the differential equation in standard form. And then the rest of it looks the same as the original Wronskian, sine of x, cosine x here. Alright. And this determinant is 0, then minus sine x secant x. Well, minus sine x times secant x is sine x over cosine x. That's minus tangent x. Alright. So u1 prime is this w1 negative tangent x divided by w, which is just 1, right, the original Wronskian. Then we integrate. So u1 of x is equal to the integral of negative tangent x dx, which is the natural log of the absolute value of cosine x. And don't worry about the plus constant here. Again, if you read your textbook, they're gonna tell you, hey, the addition of a constant won't make any difference, right? So I'm going to ignore the constant for right now. In fact, I'll write that here. Right. So we'll ignore the constant of integration. Alright, so I know the value of u1. u1 is the natural log of the cosine of x. Right. And then I'll do something similar for this other function u2 that'll be multiplied by the sine of x, and then I'll have my particular solution. Alright, so u2 prime. Right, u2 is going to be a function. Again, I'm not going to go into the development of this, just u2 prime, the derivative of u2, will be w2 divided by w, right, where w2 is again the same as the original Wronskian, but I replace the second column with the 0 all the way down to f of x, so this 0 secant x. So the original Wronskian, so down the first column I'd have cosine x, negative sine x, and then down the second column I replace that column with zeros all the way down till the last row, and then in the last row I put that f of x, which in this case was the secant of x. And this determinant is cosine times secant. That's just 1 minus 0. So this is also just 1. So then plugging those in, we got u2 prime is 1 divided by 1, or just 1. And then integrating, we get u2 of x equals, the integral of 1 with respect to x, which is just x. And again, ignoring the constant. ignoring the whole plus c or plus c1 plus c2. Alright, so now I have, u2 of x, I have u1 of x. Now I can state a particular solution to this differential equation. yp, setup here was, u1 of x times cosine x, so that's the natural log of the absolute value of cosine x times cosine x. That was, this u1 times cosine x plus u2 times sine x, and u2 is just x times sine x. And now that I have the particular solution and from earlier the complementary function, the solution of the homogeneous, we can put them together and get the general solution to the original differential equation, y double prime plus y equals secant. So the general solution to the entire original equation looks like the following. Y equals, again, the complementary function, which was some constant c1 times the cosine of x plus some constant c2 times the sine of x plus, and then the particular solution, this natural log of the cosine of x times the cosine of x plus x times the sine of x. And there you go. And here's, again, this is called, one more time, y sub c, the complementary function, the solution of the associated homogeneous equation. And then this here is a particular solution to that non-homogeneous equation. And put them both together, we get the general solution of our equation. And and this should work for any choice of C1 and C2. And I'll leave it to you to verify it. I don't feel like going through that here, but if you take the first derivative of this, second derivative of this, and then substitute, the equation will be a true statement. This y double prime plus y equals secant x. Okay. So you're taking lots of determinants here. And really these forms, the u2 prime equals w2 over w and u1 prime equals w1 over w, those came from using Kramer's rule at some point, if you recall what Kramer's rule is, from linear algebra. But again, that's neither here nor there. I am not going to go into all the development of the method. Just going to use it. Alright, so that was one example. Let's do this again. And all my examples here are going to be second order equations, so you'll end up taking determinants of 2 by 2 matrices. For a third order equation, you'd end up with 3 by 3 matrices. So higher orders get more complicated, of course. Alright, so let's do that again. So same instructions. Solve this second order linear differential equation, non-homogeneous, by variation of parameters. So again, first I'm going to look at the associated homogeneous equation. Right. Short for associated homogeneous equation. So that's y double prime minus 9y equals 0. And again, if you make the substitution y equals e to the mx, you'd get the auxiliary equation. Let's put aux, m squared minus 9 equals 0. And this has two distinct roots, right? This would be m minus 3 times m plus 3 equals 0. So my roots are, m equals 3, and m equals negative 3. And putting these together, we get our complementary function, right? The solution of the associated homogeneous equation. So yc equals, some constant c1 times e to the 3x plus some constant c2 times e to the negative 3x. Right. Now the form, here comes the variation of these parameters c1 and c2. What I'm going to do is, instead of having those be constants, I'll replace them with functions that vary depending on x, vary with x. So the form of a particular solution, yp, will look like the following. Yp equals, say u1 of x times e to the 3x plus, and then instead of c2, some function of x, u2 of x times e to the negative 3x, where u1 prime is w1 divided by w, and I'll talk about what these are in a second, these Wrons schemes, and u2 prime is w2 divided by w. Okay, so before I set up these Wrons schemes, remember this is in standard form already. So this 9x divided by e to the 3x, that's the f of x I'm going to be using when I replace certain columns in my Wrons schemes. Alright, so first let's look at w, where w is just the Wrons scheme of these two functions from the homogeneous solution, the e to the 3x, e to the negative 3x. So the determinant, you got e to the 3x, e to the negative 3x in the first row, and their derivatives, 3 e to the 3x, negative 3 e to the negative 3x in the second row, and take the determinant. So this would be negative 3 minus 3, that'd be negative 6. Right. The determinant is equal to negative 6 for any value of x. Okay. So now I know the value of w, and w1. W1 is the same Wronskian, the same determinant, same matrix, but I replaced the first column with zeros down the column all the way to the bottom of it, the last row where I'm putting this f of x back in standard form. Now instead of writing 9x divided by e to the 3x, I'm going to put 9x times e to the negative 3x, just to make it a little cleaner. That's this f of x here. And then the second row stays the same, second column stays the same, e to the negative 3x, negative 3, e to the negative 3x. And this, this determinant is 0 minus 9x e to the negative 6x. Alright. And then w2, again, same as the original Wronskian matrix, but I replace the second column. So the first column of the original Wronskian stays the same, e to the 3x, 3 e to the 3x. Then I replace the second column with a column where you have zeros from the top all the way down to the bottom row, and in the bottom row I put this f of x, which is, again, I'll write as 9x e to the negative 3x. And this would just be 9x minus 0. So 9x. Okay. So as I mentioned before, we'll start with u1. U1 prime is w1 divided by w. W1 is this, divided by w is that. So it's negative 9 over negative 6 is positive 3 halves times x e to the negative 6x. All right. Then to find u1 itself, I integrate. So u1 of x is 3 halves times the integral, we could pull the constant out, right? X times e to the negative 6x dx. And this integral here, I would do by parts. Integrate by parts. Where me personally, I would let u equal x and dv be e to the negative 6x dx. Then du would be just dx, and v would be negative 1/6 e to the negative 6x. Alright, so putting that all together, remember the integral of u dv is equal to uv minus the integral of v du. Hopefully you remember how to integrate by parts. This would be 3 halves times the quantity, uv is negative 1/6 x e to the negative 6x minus v du would be plus 1/6 times the integral of e to the negative 6, so minus 1/36 e to the negative 6x. And then again, I'm not going to worry about writing plus some constant here. Then we can put the 3 halves in. So u1, actually, you know what? Instead of putting the 3 halves in, I'm going to factor out negative 1/36. So if I do that, 3 goes into 36 12 times, and 12 times 2 is 24, so that'd be negative 1/24 pulled out, and then they both also have e to the negative 6x. I'll pull that out as well. And if I pull out negative 1/36, this first part would be 6x plus 1. Right. So I personally like that. So there's u1 of x right there. And then I'm doing the same thing to find u2. So again, u2 prime is this w2 divided by w, which, w2 is 9x, w is negative 6, so that's negative 3 halves x. And then integration yields u2 of x equals, negative 3 halves times the integral of x dx, which is just half x squared, right? So negative 3/4 x squared, and then again, don't worry about plus some constant. And now that I have u1, I have u2, I can write yp, right? So yp, a particular solution to this differential equation is, u1, so negative 1/24 e to the negative 6x times the quantity 6x plus 1 times e to the 3x, right, which I'll simplify that in a second, because it's like this, u1 times e to the 3x plus u2 times e to the negative 3x plus u2, negative 3/4 x squared times e to the negative 3x. And yeah, we can simplify this a bit. So a particular solution is, negative 1/24 times the quantity 6x plus 1 times e to the negative 3x minus 3/4 x squared times e to the negative 3x again. Right. And I guess if I wanted to, I could factor out e to the negative 3x from both of these and be left with some quadratic. You'd have negative 3/4 x squared from this term, And then distributing the negative 1/24th here would be minus 1/4 x minus 1/24th. And there's a nice, I guess, a nice way if you want to write that particular solution. And now that I have a complementary solution to the homogeneous equation, I have a particular solution to the non-homogeneous equation, we can write the general solution. Y equals some constant c1 times e to the negative 3x, e to the positive 3x, plus some constant c2 times e to the negative 3x, plus, and then this particular solution, e to the negative 3x times the quantity negative 3/4 x squared minus 1/4 x minus 1/24th. Great. And again, you can replace c1 and c2 with any constants you wish, and this would make the original equation a true statement. You can also verify it, the old-fashioned way. Take the first derivative of this, take the second derivative of this, substitute, and the original equation should be a true statement. But again, I'm not going to do that because it seems like it would take a while. But I'll leave that to you. And I guess also you could even, something I'm noticing here is that if you distribute the e to the negative 3x here, you'll have another constant times e to the negative 3x, and you can put that together with this one, make a new just constant times e to the negative 3x plus e to the negative 3x times negative 3/4 x squared minus 1/4 x, and then leave it at that. But this is totally fine as well. Okay. But yeah, same procedure, lots of determinants, right? So I'm just going to do this one more time. And this solving a differential equation through variation of parameters. Alright, so this one at the moment is not in standard form, like the previous two examples. It's not in the standard form for a second order linear equation. But very easy to remedy. Like I mentioned in the very beginning of this video, you just need a 1 as your coefficient of the highest order derivative, so I need to just divide by 3. So put it in standard form now. We have y double prime minus 2y prime plus 2y equals 1/3 e to the x secant x. Alright, so now it is in standard form. And so this expression over here, right, the 1/3 e to the x secant x, I'm going to consider this the f of x that I have mentioned in the previous couple of examples, right? Alright, so just like the others, I look at first the associated homogeneous equation, which would be this: y double prime minus 2y prime plus 2y equals 0. And I'll just tell you right now, I would let y equal e to the mx. Here we have a homogeneous equation with constant coefficients. And then we get the auxiliary equation. I'll just put AUX, or a characteristic equation. M squared minus 2m plus 2 equals 0. And this isn't nice and factorable. I could solve this with completing the square or quadratic formula. This is actually m squared minus 2m plus 1 equals -1, which is m minus 1 squared equals -1. So my roots, right, the roots here are m equals 1 plus I and 1 minus I, right, complex conjugates. So the general solution to the associated homogeneous equation, right, this complementary function yc, is going to be this. Some constant c1 times e to the x cosine x plus, and then some constant c2 times e to the x sine of x. Right, so, and then I'm going to be using these two independent functions, e to the x cosine x and e to the x sine x. I'm going to be using those when I set up my Wrons Scheme in a little bit. Alright, so I've got the complementary function, the complementary, the solution to the associated homogeneous. So next come, finding a particular solution to the non-homogeneous equation through variation of parameters. So again, I'll write, variation of parameters. We are varying the parameters c1 and c2. So the form of the a particular solution that we're looking for, yp, is going to again be some, instead of c1, some function u1 of x times e to the x cosine x plus, and then instead of c2, right, some function u2 of x times e to the x sine x, where u1 and u2 satisfy the following. U1 prime is w1 divided by w, and u2 prime is w2 divided by w. And again, I'll state what w1, w2, and w all are. So again, w is a Wrons Scheme. It's a determinant, and it's the Wrons Scheme of these two functions from the complementary function, right? E to the x cosine x and e to the x sine x. So I have e to the x cosine x, e to the x sine x in the first row, and then the second row has, their derivatives. Now, this would be, e to the x times negative sine x plus cosine x e to the x. So it's e to the x times cosine x minus sine x. Right. And then the derivative of this would be, e to the x times cosine x plus e to the x sine x, pulling the e to the x out, it'd be e to the x times, cosine x plus sine x. Sorry about the tightness here. Should have opened that up a little more. This is cosine x plus sine x. Alright, taking this determinant, this would be, let's see, we have e to the 2x times cosine x times cosine x plus sine x minus, and then e to the 2x sine of x times cosine x minus sine x. Let's see what we get when we simplify here. So they both have e to the 2x in common. Pull that out. And then distributing the cosine, we'd have cosine squared here, and distributing the negative sign, we'd have, plus sine squared x down here, that'd be 1. And then you have positive sine x cosine x minus sine x cosine x, so that's times 1. So that's just e to the 2x. The Wrons Scheme for those two functions, this determinant here, is just e to the 2x. All right. Now, w1 is the same Wrons Scheme, only the first column is replaced with 0 and f of x, right? 0 is down the column, and then f of x is this, 1/3 e to the x times the secant of x, and then the second column stays the same, so e to the x sine x, and then e to the x times the quantity cosine x plus sine x. Oops, sorry about that, you're not able to see that. So 0 f of x, and then the second column stays the same. Alright, now if you do this determinant, it would be 0 minus, and then so we have negative 1/3 e to the 2x times tangent x, because sine times secant is tangent. Alright, so there's W1. And then I do the same for W2, only replacing the second column with 0 and 1/3 e to the x secant x. So W2. Keep the first column the same now, so e to the x cosine x. And then this e to the x times the quantity cosine x minus sine x. And then 0 f of x, 1/3 e to the x secant x. And doing this determinant, we'd have 1/3 e to the 2x minus 0. So just 1/3 e to the 2x, right? Because cosine times secant is 1. Okay, and going back up here to the W1 over W, W2 over W for U1 prime and U2 prime, we get U1 prime is W1 over W, which is negative 1/3 e to the 2x tangent x divided by e to the 2x. So the e to the 2x was cancel. I have negative 1/3 tangent x, and then integrating and ignoring the constant of integration, U1 would be 1/3 times the natural log of the absolute value of the cosine of x. Alright, because remember the derivative of natural log of cosine would be negative tangent. So that U1 is 1/3 the natural log of cosine. And U2 prime is W2 over W. W2 is 1/3 e to the 2x divided by W, just gets rid of the e to the 2x, is simply 1/3. And this makes this even easier. So U2 of x is just 1/3 x. And then putting those back into my form of the particular solution to this equation, we get yp. So yp, the particular solution to this equation, is u1 of x, so 1/3 times the natural log of the cosine of x times e to the x cosine x plus u2 of x, which is 1/3 times x times e to the x sine of x. And there's the form. There's a particular solution to this equation, and you can double check it. Take the first derivative and second derivative of this yp and plug them into the equation, and it will make the original equation true. I promise you that. You can test it out. Again, I'm not going to really do that here. A lot of product rule stuff. Don't really feel like taking the time to do that right now, but you can if you want, to verify that it is indeed a solution of that original equation. And now that I have a particular solution and also the complementary function, right, the general solution of the associated homogeneous, we can now state the general solution of my original differential equation. Right? So the general solution looks like the following. Y equals that complementary function, which is c1 times e to the x cosine x plus some constant c2 times e to the x sine of x plus our particular function, our particular solution. I'll just put yp. Okay, so write all this right there. Alright, and this is for any constant. Again, you can verify this by taking the first derivative, taking the second derivative, plugging in, substituting into the equation, and it should make the equation true, right? Should end up being a true statement. Right. Yeah. So hopefully you noticed that it was pretty much the same procedure every single time. Where I find these Wrons schemes, and then once I have all the Wrons schemes, I divide W1 by W, W2 by W, and integrate for U1, U2. And there would be the same. You'd be doing the same thing for a third order or fourth order, just with a 3 by 3 matrix or a 4 by 4 matrix instead of a 2 by 2, right? These were all second order equations, so you're just ending up taking determinants of 2 by 2 matrices. So obviously the higher order equation, the more involved the determinants will get. All right. So find the solution of the homogeneous equation. Change the constants in that solution to functions of x, functions of the independent variable. There's your variation of parameters. Then find all those Wronskians and do the division and integrate, and you'll have your particular solution. Then take your general solution to the homogeneous, add the particular solution, and there's the general solution of the original differential equation. All right. Oh, and of course, right, make sure that the original differential equation, make sure you put it into the standard form for an nth order linear differential equation before you continue on. All right, so again, a lot of stuff doing there, but hopefully watching me go over these few examples help you out when you're working on problems like this on your own. And thank you very much for watching.